So what are branching programs? And that's what I'm going to start with. Before I start with branching programs, I'll start with, in some sense, an even simpler way to think about computation, which are decision trees or query algorithms. So here we start, it's a tree, you query, you have an input of variables, they're Boolean variables, and you have a node that's named by a variable you're going to look at. You're going to look at x1, and you're going to, based on what you've seen so far, you're going to choose another variable to query and so on. And this is an example of a decision tree to compute the parity of 4 bits. It happens in this case that the order in which variables are queried, or input variables are queried in the program, happen to be the same. That's not required for a decision tree. So, and so you can see there's you keep querying, at the end you get the value of the function at the leaf of the tree. So for example, if x1 is 1 and the remainder are 0, you end up with, at this node, which is this node, right? And you've correctly computed the value of the function. Now, you'll notice something about this particular tree. For example, we have 2 subtrees that are exactly identical. Okay? And these 2 subtrees are also identical. So it's wasteful to include them both in the description of the function. And if you start doing that, and you realize rather quickly that a decision DAG, a decision acyclic graph for parity, is a much better way to go. Where on the left side, you're essentially, as you're going along, you'll remember I've seen 0 parity so far. On the right side, you remember I've seen 1 parity so far. For decision trees, doesn't matter what order that you do things, the size is essentially what I described on the previous slide. So this is a decision DAG, and it's known by 2 different names in 2 different communities. One is branching programs, which is what I'm going to use, and the other is BDDs, or binary decision diagrams. If you've been in coding theory, you might have seen that as well, or if you've done anything with verification. So this dual terminology has some history. In fact, the first versions of things that were like branching programs go back to Shannon and switching networks in the late 1940s. And Necheporek actually proved the first lower bounds for something he called contact schemes, which are variants of switching networks. The terminology branching programs originates in a PhD thesis of Maciek from 1976, and his goal was to get a simple model that would capture both time and space complexity at the same time. A little bit later, but in parallel, the terminology binary decision diagrams arose in a paper by Akers. And their goal was, and there's an earlier paper that didn't use the terminology, and the goal was a convenient representation of Boolean functions, just like we found a convenient representation for the parity function. There was an extension from the Boolean case to multi-way case and with multi-outputs by Borden and Cook, who proved the first time-space trade-off lower bounds for general models of computation. And we'll actually go through that basic property, those basic properties. And there's a famous theorem known as Barrington's theorem, which we won't go into at all, about branching programs in '86. The binary decision diagram terminology really took off with work by Bryant, who showed that if you restricted them to be ordered binary decision diagrams, and I'll go through what that means, then they were very convenient for verification. And these restricted versions are sometimes called trellises and come earlier in the coding theory literature, but there are a lot of reasons why Bryant's paper is known. The O actually is important. Akers' paper defined a fully general model, although he probably thought mostly about the a special case, somewhat like Bryant's, but often that O is omitted when they're discussed in the literature. So if you see BDD in the literature, very often what they mean is just this restricted form. They're usually, in general, BDD-related models, and their variants are more restricted than the branching program models we're going to talk about. And in terms of the terminology, branching programs tend to be used in the complexity literature, and BDDs, binary decision diagrams, are used in formal verification literature. So I don't know how many of you have actually seen BDDs at all? Okay. So we're going to focus on this motivation for branching programs, which is a simple combinatorial model that captures time and space simultaneously. So what do we mean by space in a computation? So here is a standard offline Turing machine model. You have a read-only input and a write-only output. You have some finite control and some number of work tapes. Okay, so and you can read and write on the work tape. So the normal notion of space in Turing machine is how many cells on the work tapes did you actually use? The input, that's read-only, we don't count that. So in general, space could be much smaller than the input size for Turing machines. The other natural model, which is more like a standard programming model, is random access machines. And there you have a program. You have registers, so this is an array of registers, and you can read in inputs. So you can do indirect addressing and things like that. So in order to read in an input, your words of memory have to have at least log-in bits, because you have to have an address. You have to be able to address that. And you have the usual indirect addressing, standard operations, looping structure, and the only state within the program is the program counter. So again, write-only output. So how do we measure space here? Well, we're going to measure space in bits as opposed to words. So we think of a word as C log n bits long. So when I talk about space for random access machines, we're typically going to talk about the total number of bits it takes to encode it. Time, you get to operate on log n bit chunks in a unit of time. So that's the model. And for both of these models, we have a notion of a configuration, which is a snapshot of the computation. So what's this snapshot? It's everything but the read-only input and the write-only output. So it's the state of all the pointers for where the heads are. It's the contents of all the tape. It's the state of the machine. So it's everything but the input and output. And that same thing also holds for the RAM. So that's the program counter plus the contents of the storage. Okay? So that's a configuration on a machine. And now we can talk, once we have this notion of what a configuration is, we can define a graph given our machine, whether it's a Turing machine or a random access machine, that describes the behavior of that machine on all inputs of size n. Okay? So some of you may have seen Turing machine graphs where you actually fix the input. Here we're going to look at a graph over all inputs of size n. So you're going to have one node. So if it uses space S of n, it's going to have one node per configuration of up to that size. It'll be labeled, the node will be labeled by what input position you're next going to read from that configuration. What are you going to read in that configuration? And there's going to be an edge from one configuration to the next, depending, and of course it's going to depend on the value read, and it's going to say, based on that value, so there'll be an out edge for each of the possible values of xi. So there are only two if it's Boolean, but we'll also consider the case with words, leading to the next configuration. And that can depend on the value. So we've got configurations. Each configuration queries an input and branches based on the value to say what the next configuration is. The start node is the generic initial configuration of the machine, and the halting configurations will be sync nodes in this graph. Now, as we've described, and the number of nodes, because of the way we've counted space, if we have a space S of n and S has to be at least log n, the number of nodes is exponential in the space. Okay? For both Turing machines and RAMs. And we can, without loss of generality, because it doesn't cost much to count steps, we can add a step counter in all of our models, and that will guarantee that this graph is acyclic. Okay? And that's going to increase the space by almost a constant factor. What do you get out of that? You precisely get a branching program. So here is a generic branching program. We've got a graph. Notice it's possible to have paths where the same variable, x2, is queried more than once on a path. There's no specific order on which these things are read. Okay? And if we get an input, it follows a path in the graph to an output just like it would do with a decision tree. So it follows a unique path. Now what are our key measures? So time is going to be the length of the longest path from an input to a sync node to a halt. That's the length of the longest computation. And space, because remember the graph was exponential in the space bound we started with, we want to match that. We're going to define space to be just log base 2 of the number of nodes in the graph. It takes that many bits to represent a node in the graph. So this, it's a very simple, clean model, captures time and space together. Now, for Boolean case, this is good. If our output is, say, just a bit for the function we want to compute, that's great. Sometimes in random access machines, we think we've got a graph. You read in a node name, something like that, where log n bits is a nice notion of a word. So we could have a multi-way version, and let's say that the values are between 1 and m. So you've got m different possibilities for your multi-way branching. So we can generalize it, but it's too hard to draw for anything terribly large. And some other things, because we added this counter, we know something a little bit more about the branch room. It's leveled without loss of generality. Any edge goes from one level to the next level, which corresponds to the time step. Okay? So that's the form for decision problems. What happens if we want to compute lots of outputs? We don't want to have a single leaf for every possible output vector. So, yeah?
You said it was leveled. I'm confused about that because you have a counter, but couldn't there be some parts where you're merging things together in a program that is not out of sync?
So, remember when we've added a counter, that counter goes up by 1 per time step.
That's part of the description of the machine.
Each node has the counter in it.
Okay.
And so the counter is going to go up by 1. And so we can partition the nodes based on the value of the counter. And it doesn't cost us in space in any significant way. Okay? So that's the basic branching program for Boolean functions. But if we want to have many output functions, it's convenient to have outputs just a single sync node and to allow outputs to be produced along an edge. So if you go along this arc, y1 gets, the value y1 gets set to 1. You can even produce multiple outputs along a single arc. Okay? So that's the model. We now just have one sync node, and so we didn't have to have a separate node for it. So this is the multi-output version that was defined by Borden and Cook. So this really does capture time and space on Turing machines and on random access machines. And we can, I hope I've given you the information to realize that this is correct. So if f is computable by time t of n and space s of n by a Turing machine or RAM, again, we need the space to be at least logarithmic, because in order to read the input, we're going to have at least n nodes. And so the space by our measure is always going to be at least log n. F on inputs of length n can be represented by a branching program of time t of n and space order s of n. Okay? So the space might go up by a constant factor, but it pretty much represents exactly what's going on. So there's some things, for example, that we can get as immediate corollary. If you can show somehow that your function does not have a polynomial-sized branching program, then that means it cannot be computed in space order log n. Okay? Now proving such a thing is beyond our current capabilities in complexity lower bounds. We don't know how to prove for most functions except for p-space complete functions. There's certainly problems in NP. We're not able to do such things. So even showing that things require polynomial size or large polynomial size is not an easy thing. But one thing I also want to mention, branching programs are much more powerful than either RAMs or Turing machines. Because we don't care how the internal memory is organized. All these operations, any operations that just changes internal memory and ignores the input for a step, that doesn't cost anything on this model. Okay? So what do we know about branching programs? Well, there's some simple things. If your function takes n bits, then always we can create a decision tree just like we did for parity that's of exponential size, 2 to the n size, and has and has depth n, reads each variable at most once in order. So time is at most, so time n and size 2 to the n is possible. Well, size 2 to the n corresponds to space n, okay, because space is log of the. So the really relevant space bounds are going to be between log n and n. Do you need space n or linear space, which is an exponential size branching program, or can you get away with logarithmic space or polynomial size? Okay? You need that S of n bigger than equal log n just to read the input. And notice if we have a multi-way one where there are m values per input, you can actually get slightly larger space bounds. And log base 2 of m would be the space for that decision tree. So key questions are space lower bounds, like pure size lower bounds, trade-offs between time and space, which we'll do mostly, and maybe like the OBDD, special classes of branching programs with good properties. So the outline of my talk is going to be some basic size lower bounds. I'll talk about multi-output functions this hour. We'll get time-space trade-offs for general branching programs. I'll talk about the relationship between them and data structures, lower bound methods, and even time-space trade-off lower bounds for encoding good error-correcting codes. So that's the plan. So I'll start. Yeah. Yeah.
You can also prove lower bounds in the width without proving log n.
So I'm not going to distinguish width and space because of the transformation that we did to layer the branching programs. The width of the branching programs that I'm going to start with is always going to be comparable to the space, just because of the trick we did. But you can.
Pointing out that there are some other there might be interesting results that one could hope to prove that are easier than this
But by focus, so yes, so that's right. So Barrington's result said that if you had only constant width, then you can actually get, surprisingly, you can get polynomial size branching programs for anything that has a polynomial size Boolean formula. So I'm not going to talk about that. That's a nice question, but I'm skipping over that for today. So we can, however, prove true space size lower bounds, and that goes back to Shannon. So the early stuff, we're going to get some nice things. So the claim is that if you have a function, a Boolean function on n bits, and its size is at most s. I'm using little s for size. That's exponential in the space. Okay? It's a little opposite how you might think, but anyway. And the claim is there aren't too many of them. Well, how can you do this? Well, each branching program is specified by It's on n variables. They're n to the s ways of labeling the nodes, the n nodes of, s nodes of your branching programs by the variable that's queried at them. The node names reached by 0 and 1 out edges, well, we have a 0 and a 1 sink, so we're not counting those. So we've got s minus 2 of those. There are s of them on 0 and s of them on 1. So we get this. We have to name the root where you started. And now we observe that this naming convention was somewhat arbitrary. So there are s factorial ways of permuting the names, and we get essentially the same function. So we take this n to the s times this divided by s factorial, and you get ens to the power s. Okay? Just using that s factorial is at least ne over s to the s. Pardon? E is the base of the natural log, n is the number of variables, s is the size. Yeah. So from this, we can get the following theorem. This almost all Boolean functions require size 2 to the n over n minus little o of 2 to the n over n. In fact, there are upper bounds that say you can actually achieve this. So remember we said 2 to the n is the biggest for the size you could have. This says you need 2 to the n over n, almost that much, which is space n minus log n. And it's a simple counting argument. So the number of different functions on n bits is 2 to the 2 to the n. And if you want to capture at least 1 minus 1 over n of them, then your number of, in size s, the number of function, you got to be bigger than this, right? So, because this is only a 1 over n fraction of functions would have size smaller. So we need ens, which is to the s, which is the size of the number of different functions you can compute in size s, to be at least double exponential in n. And if you just solve that, you can just see at the first that s has got to be not too far from 2 to the n, pretty easily. Okay, so that gives us a lower bound. It says lots of hard functions exist. Almost all functions are hard. Those are random functions. What about explicit functions? So I'm going to describe the best bounds we know for explicit functions. In order to do that, we have to see this question about what it means to restrict a branching program. So if I take this branching program, which computes some function, and I say, I'm going to tell you for sure that x1 is 0, then I know that certain edges will not be taken. Okay? So these x1 nodes, the other edges, the edge when x1 was 1, is not taken. And now, of course, I don't need to query it anymore, so it can eliminate those nodes. And I get a reduced branching program. So this branching program computes a subfunction of the original function, the subfunction that you get when you set x1 equals 0. Notice this part is now irrelevant, but we're going to ignore that fact. This node can never be reached. These two nodes can never be reached. We don't care. So we can repeat restricting more variables to get other functions. And the key thing to observe is the remaining branching program has a subset of the original nodes where the restricted variables have been removed. So there's no x1 in this program. If we did more, but they're the original nodes. Everything else is the original nodes. We've just taken out those other nodes and short-circuited. So here's the function that we're going to show is hard, is the element distinctness function. So this takes n numbers in the range 1 through m, which we could code in log base 2m bits each. So think of this as a Boolean function on this many inputs. And it's going to be 1 if all of those n numbers are different. Okay? Because I'm going to want to talk about the total number of bits as the parameter, I'm going to use capital N for the size of the numbers. Okay? And let's imagine that each of the numbers is between 1 and n squared. Okay? So look at what happens. Say how does this depend on x1? What are the different ways when I set all of the remaining variables, x2 through xn, to some other value? Well, if I've set x2 to x3, if I've set those to the same value, it doesn't matter what the value of x1 is. The function is 0 because it's not the case, x2 equals x3, so it can't be all different. But if I have set them all to different values, so I've set x2 through xn all to different values, then there are capital N minus 1 values that are bad, that I have to avoid. Okay? Now, how many different ways could I set x2 through xn to n minus 1 different values? Well, that's n squared choose n minus 1, which is at least n to the n minus 1. Okay? So when I fix all but one value, and this is the same for x1, x2, whatever, when I set all but one value, there are lots of different ways I could restrict the remaining variables and get different subfunctions on just this one variable that's remaining. It's a real lot. And in fact, this is roughly the biggest you can get for functions of this size, which is one reason why we picked the element distinctness function. Necheporek, by the way, who used this, titled his paper A Boolean Function. But in fact, he didn't use this natural function. He used something else. But the claim is that if we want to compute this, we're going to need size capital N squared at least, which because the total number of bits is 2n log n, because it takes 2 log n bits to represent a number between 1 and n squared, we get an n squared over log squared lower bound. Okay? And the proof is just going to use the Shannon argument. So let's start with a branching program for this element distinctness function. And break up the input into blocks, b1 to bn, of 2 log n bits each. So each of these blocks is one of the n numbers. So it's a block of bits, so think of that as a set of bits, and it corresponds to one of the n numbers. And let's let Si be the number of nodes of this thing that have variables in bi. Little si just says how many of them were bits of the ith number. So there are 2 log n bits as input. There are 2 log n bits there. And its size is at most si. So I'm just plugging in 2 log n into our previous formula. That's the number of different functions, different subfunctions we could represent by setting all the other nodes of the branching program, all the other variables, the branching program arbitrarily. So there are that many distinct functions that you can get just on that subset of variables. But that number of subfunctions is at least n to the n minus 1. So we need this quantity to be at least this quantity. So pretty clearly you can see that Si has to be some linear function of n, capital N, and certainly it's bigger than capital N over 2. Okay? But these are a subset of nodes that only talk about variables in bi. There's a separate subset for each I. These are disjoint subsets. So there are n choices for I, so we get at least n squared over 2 nodes in the program. And that's the proof. This is still the largest size bound known for any explicit function. Okay? Despite this simplicity, it goes back to 1966. That's the best we know for just pure size for any explicit function. Okay. That's sort of good news and bad news, the very bad news. We're going to have lots of good news now. And these are really nice time-space trade-outs for multi-output functions. So what do I mean by multi-output functions? They're functions like sorting. So you got n numbers in the range 1 to n squared, you want to produce their sorted output. Or you have a fixed matrix A, which is not part of the input, the algorithm knows it ahead of time, and you want to compute the linear transformation A times x. An example of such a transform is the discrete function is the discrete Fourier transform, where you take the DFT matrix or and multiply it by x. And we know reasonably efficient methods to do that. Convolution and integer multiplication, matrix multiplication, generalized string matching, and computing universal hash functions. All of these take lots of inputs, lots of outputs, and we can get lower bound trade-offs for all of these. So I'm going to focus just on this one example of this problem, and in particular I'll discuss the discrete Fourier transform, since that might be interesting to both sets of the audience. Now it's known, you might wonder, if you've got an n by n matrix times an n vector, how could you possibly do this efficiently with small time, better than n squared? Well, in fact, discrete Fourier transform, we can do computation in time, well, is n log n, at order n squared over s. So as with large space, we can get n log n time. But if the space is only log n, it takes us near n squared time. Okay? And here's the algorithm. So this is the FFT graph, or the butterfly graph. So if we go back, if you're telling me a space-bound S, the general idea is go back log S elements here. So now they're S nodes. So this is a tree of, there are S nodes here. And the claim is in one pass, in space S, I can compute all of these outputs. And the general idea is you just go through. So with S, so we're going to have space for each of these and a space for the height. And you just sort of walk up combining. As you scan along, you can fill out the values for these nodes. And so in space S and a single pass, you can compute S output. And now we just do this n over s passes in total, and that gives us the bound. Okay, so that's the upper bound. It just says you can get behavior like n squared over s. We're going to claim that that more or less is optimal. Okay? And the key property of this discrete Fourier transform matrix, which we will not prove, that it satisfies, is if I take a subset, and this is not necessarily a contiguous subset in either rows or columns, so it's some submatrix that has at most n over 4 rows. So in the case of DFT, it's an n by n matrix instead of an n by, it's a square matrix, and at least 3n over 4 columns. So not too many rows and lots of columns. So there are not too many columns left out. Then, no, so there are only n over 4 rows. There are lots of columns, so the left out portion is small. In that case, this matrix has full rank, which is the number of rows. So it's a non-square matrix, and it doesn't matter what that is. And we're going to call a matrix which has this property where the number of rows is, so in general it's an m by n, where the number of rows is, that we're looking at is at most a beta fraction of the possible rows, and at least a 1 minus beta fraction of the columns. We're going to call it beta hard. Okay? So in this case, beta equals 1/4. So here's the definition again. So I just copied it over. And the key lemma is that if you have a matrix A, which is beta hard, then for any fixed assignment to at most beta n entries of x, and if you're looking for, that's of the input, and if you're looking for at most beta m, a beta fraction of the outputs, then the probability, if you fix both of those, fix small number of inputs and a small number of outputs, then the probability that you get those outputs, given that you agree with the inputs, is exponentially small in the number of outputs you're looking for. And the proof in this case is kind of a proof by picture. So here is the blue parts are the parts that fix. These are the outputs that you're looking at. This is the B. The A is this part here. Okay? So look at the rows of the matrix that correspond to the outputs and the columns that correspond to the parts you haven't fixed in the inputs. Okay? So look at this. You get these outputs if and only if this is an equation in the colored stuff. This is fixed ranks k. This is variable. You can see it's basically k equations, full rank system of k equations, q to the minus k is the probability that you get any fixed answer. So very nice. And that's the only property of the problem that we'll need to make it, to say that that gives us a time-space trade-off lower bound. So the claim is if you're going to compute an m by n matrix vector product where the matrix is beta hard, you're going to need time mn over s. So time-space product is n squared, for example, for the DFT. And the proof method was introduced by Borden and Cook actually for the sorting problem. It's a little cleaner for this problem. And the basic idea is to use the number of output values as a measure of progress. And what you're going to say is if the branching program is short, if t is small, then for each input we can identify progress in a small piece of the branching program, and that piece is going to be associated with a single branching program node. So each input, there's a single branching program node which describes a small piece, which will say we make lots of progress on that input. And then we're going to prove, and this is where the key lemma will come in, each piece can have large progress for only a small number of inputs. Since progress was associated with a node, and each input has only a small fraction of the inputs, we're going to need lots of nodes. So if time is short, then you need lots of nodes. So here's the picture of the diagram. So we're going to pick this same beta, which has to do with the hardness, and we're just going to look at the branching program broken up into layers of beta n time steps. Okay? So this is the time is capital T, beta of n is the difference between each layer. And consider the behavior on some input x. It goes through the branching program, and it hits some node at the boundaries between each of these layers. And we're going to call that sequence of nodes at the boundaries between layers the trace of the input. Okay? That's the yellow nodes. That's the trace of the input. Okay? Well, how many layers are there? So let's let L be the number of layers, and it's T divided by beta n. Okay? So the branching program has to produce m outputs on every input x. Right? So one of those layers it has to have produced a lot of outputs. So m divided by L. And m divided by L, when we plug it in, is beta mn over t. Well, let's just call that k. That's going to be the same k as the previous thing that we're talking about. So k is going to be the number of outputs you produce in at least one of the layers. We don't know what layer that is. So one way to think about it is there's this, if we look at the nodes of this branching program, and we look at the nodes of the branching program that are reachable from that trace node in the layer L where lots of outputs are going to be produced, look at that little mini branching program, just that little piece of a branching program. In that piece of the branching program, X is going to have lots of output produced. It's going to have K outputs produced. So it's this mini branching program rooted at the node, the V sub L, the node in that, for the Lth layer in the trace, produces K outputs on input X. Okay? Now, I've said there has to be one. It's got to be one of these, but we don't know which one. So there are only these branching programs. So that's for this particular input X. Over all inputs, there are lots of others. So each one of these little nodes at these layers is going to work for some input. So, and how many of them are there? Well, there are at most 2 to the s nodes in the branching program. So in total at the intermediate layers, there are at most 2 to the s nodes at these boundary layers that could be nodes in the trace. So for every input, not just our input X, there's got to be one branching program, one of these little mini branching programs that produces k outputs, lots of outputs on that input. Okay? So let's just summarize. So every input has a mini branching program of length beta of n that produces k, which is beta m over t, correct outputs for input x, and then most 2 to the s such mini branching programs together must do this for all inputs. Okay? Now, I'm going to state a lemma, which we haven't proved yet. I'll prove it on the next slide. That will be enough to give us the bound. So the claim is if this matrix is beta hard, then the probability that a mini branching program of length beta of n can actually do this, or the number of inputs that it can do this correctly, is at most q to the minus k fraction of all inputs. So this says each little mini branching program only works for a q to the minus k fraction of all inputs. Okay? So let's take that as given. Here's the proof of the theorem given the lemma. There are only 2 to the s of these mini branching programs. Each is going to work for only a q to the minus k, which is a q to the minus beta n over t of the inputs. So in total, it's got to work for all of them. So the fraction, just by a union bound, the fraction of inputs for their work has to be at least 1. So 2 to the s times q to the minus beta m over t has to be at least 1. Bringing to the q to the other side, taking logs, we get that s is at least beta m n over t, and there's even a log q in there, okay, which I didn't mention before. And so that's it. Space is at least beta m over t. I just stated it the other way by swapping t and s. Okay? So the only thing we have to prove is this property, which talks about mini branching programs. What can a short height branching program do? So that's that same lemma. And we know within one of these mini branching programs that each input follows a unique path. So it suffices to show this property for each path separately, conditioned on following that path. So look at the fraction inputs that follow this path. If that's most q to the minus k, and for this path it's at most q to the minus k, since they're disjoint, those events are disjoint, the total is going to be q to the minus k. But what does it mean to follow a path in the branching program, in this mini branching program? You've looked at beta n inputs, don't care, those have been fixed, and you've produced k outputs. So it fixes k output values and beta n input values. Well, that's exactly what our key lemma said. If you fixed beta n input values and asked for k output values, the fraction of things that you were correct on was 1 over q to the k. So this immediately produces the lower bound. And so that's it. We're finished with the proof. Okay? We've got the proof of beta mn over t for space, or t is mn over s. Some general comments about what you need to make arguments like that work. So maybe for your function, some outputs are easy to produce. In this case, every output was equally hard to produce. And so you need a notion of tough outputs. You need a probability distribution over inputs. In this case, we picked the uniform distribution. And what you generally want to say is the probability I've used k tough outputs is, so you want to say that tough outputs you're going to have lots of them. You can, in general, essentially do this argument, even if it's not the case that every output is hard, and it's not the case that, but you need this sort of probability that, given you know some inputs, the probability that you agree on hard outputs is somehow exponential in k, and then you get a time-space trade-off lower bound of this form. And notice something, that we only enforce the space lower bound periodically. We didn't even care what happened inside between the layers in the branching program. And sometimes that's useful for understanding when it's going to be easy to prove things. So by these same methods, you can get time as n squared over s for sorting and unique elements, matrix vector product in DFT, that's the argument I just described. You can use the same things for convolution integer multiplication, generalized string matching, decoding good error correcting codes. has the same property. If you have a function where think of a typical streaming algorithm, but you insist on getting outputs for every window of length n, if you want to compute the frequency moments exactly, you need that. Universal hash function computation, even matrix multiplication. This is a slightly different form, but notice when space is small, you get t nearly n cubed. So some open problems. Well, for at least for the first hour. Prove an n squared size lower bound for any explicit Boolean function. The best we have is n squared over log squared. And two others that I like. Well, this one we're going to talk about some more. It's sort of a whet your appetite. We'll finish early. One is encoding asymptotically good error-correcting codes. We'd like to get a lower bound. Believe that if you want to do this so this says if you want to do things in linear time, you need linear space. I mean, that's more or less what all of these lower bounds have been saying so far. So that says you need a lot of space to get fast algorithms. It turns out that Basi-Mitter proved a lower bound, which says if you want to do things in linear time, you need log space. But if I give you very little space, it still says you can do it in n log n time. N log n over log log n. It doesn't rule out being able to do it in sub n log n time. So again, if space is small, n to the 1 minus epsilon, this gives an n log n over log log n time lower bound. So you can't do it in linear time. But if you're up at linear time, it says you can, it allows linear space. And we know there are codes which are linear time and linear space, good codes like that. And if you wanted to do element distinctness, for example, rather than frequency moments, it turns out the multi-output doesn't help. So it's just like a single output problem. That's kind of a fun one on the data structure side. So yeah, so that's all I have for the first section. We'll talk about single output functions and applications of code in the next two sections.